Look at these two docks, same lake, same wind events, same afternoon, completely different water conditions. The dock on the left is taking a beating, waves rolling in continuously. The dock surging against its anchoring system, boats at the slips getting pushed and banged around. The dock on the right is sitting in water that is almost flat. Same wind, same fetch, same storm. The difference is a wave attenuator, a floating barrier positioned upwind of the dock that intercepts incoming wave energy before it reaches the dock, the boats, and the people using both. Most lake homeowners have never heard of wave attenuators. Most marina operators couldn't run their facilities without them. And there's a growing middle category, private docks with significant boat assets, vacation rental properties, exposed shoreline configurations, where a wave attenuator is the difference between a dock that functions well and a dock that is constantly fighting conditions it was never designed to handle. Today I'm walking you through everything you need to know about wave attenuators, what they actually are, the physics of how they work, the different types and configurations available. When a wave attenuator makes sense for a private dock application, what they cost and how they're installed and maintained. I'm PJ Garola from Pennyvale Docks. Let's get into it. A wave attenuator is a floating structure designed to reduce the height and energy of waves passing through or around it. It's positioned in the water between the source of wave energy, the open fetch of the lake, and the structure or area you're trying to protect. The word attenuate means to reduce in force or intensity. That's exactly what these structures do. They don't eliminate waves completely. They reduce height and energy to a level the protected dock and boats behind them can handle safely and comfortably. What a wave attenuator is not a breakwater. A breakwater is a rigid, typically massive structure, concrete, rock, or steel, that blocks wave energy by stopping it completely. Breakwaters are fixed to the bottom, enormously expensive, and essentially permanent infrastructure. They're appropriate for large harbor and port applications. They are not what most lake dock owners need or can practically install. A wave attenuator is a floating, flexible, comparatively lightweight structure that achieves wave reduction through different physical mechanisms than a breakwater, and can be installed, relocated, and removed in ways a breakwater never can. The floating advantage. Because a wave attenuator floats, it rises and falls with water level fluctuations. A fixed breakwater that works perfectly at normal pool becomes partially submerged during high water events, allowing wave energy to overtop it, or sits too high during low water and creates navigation hazards. A floating wave attenuator maintains its effective freeboard relative to the water surface, regardless of water level changes. For lakes with seasonal water level variation, this is a significant functional advantage. Understanding how wave attenuation works physically helps you evaluate attenuator options intelligently rather than just taking the manufacturer's claimed performance numbers at face value. Waves carry energy. That energy travels through the water as a combination of vertical water movement, the up and down motion you see at the surface, and horizontal orbital motion beneath the surface. The deeper you go below the surface, the less orbital motion exists. At a depth equal to roughly half the wavelength, the wave orbital motion is essentially zero. This depth is called the wave base. The most important physical variable governing attenuation performance is the relationship between attenuator draft depth and the wave period of the waves you're trying to attenuate. Draft is the depth of the attenuator below the water surface. Long period waves, or waves with a long distance between the crests, have deep orbital motion. An attenuator with shallow draft sits above most of that orbital motion and allows most of the wave energy to pass underneath. Short period waves, however, choppy, steep, wind-driven waves with short distances between crests, have shallow orbital motion. A moderate draft attenuator intercepts most of that orbital energy effectively. This is why wave attenuators perform very well against locally generated wind chop, the wave type most common on island lakes, and perform less well against long period swells. On most island lakes, locally generated wind chop is the dominant wave type. That's a favorable match for floating wave attenuator performance. A wave attenuator works through three mechanisms operating simultaneously in different proportions, depending on the attenuator design. On reflection, on the left, some wave energy is reflected back toward the wave source by the face of the attenuator. A wave hits the attenuator and a portion of its energy bounces back the way it came. Reflection is more effective against shorter, steeper waves than against long, low-period swells. Absorption. Some wave energy is absorbed by the attenuator structures itself, converted to heat through friction and internal material deformation. Foam-filled attenuator sections absorb energy through compression of the foam core. Hollow attenuator sections with internal baffles absorb energy through turbulence created as water moves through the baffle chambers. On transmission, wave energy that is neither reflected nor absorbed passes through or under the attenuator as transmitted wave energy, reduced in height and power but not eliminated. The ratio of transmitted wave height to the incident wave is the transmission coefficient. A transmission coefficient of 0.3 means 30% of incoming wave height reaches the protected side. A transmission coefficient of 0.1 means 10% passes through. Lower is better for protection performance. Wave attenuators come in several distinct structural configurations, each with different performance characteristics, cost profiles, and appropriate applications. These are floating pipe attenuators. The simplest wave attenuator configuration is a line of large diameter floating pipes, typically high density polyethylene, chained or connected together and anchored in position. The pipe diameter determines the draft depth and therefore the wave period range the attenuator addresses effectively. Pipe attenuators are low cost, simple to install, and easy to extend or reconfigure. They perform adequately against short period wind chop and are commonly used for basic marina perimeter protection and small private dock applications where budget is the primary constraint. The limitation is performance against anything other than a very short period wave. A pipe attenuator with 18 inches of draft addresses wave periods up to about 2 seconds effectively. Wave periods longer than that pass largely underneath. Pontoon-style attenuators use larger, more complex floating sections, typically modular units that connect end to end, with greater draft depth, higher freeboard, and internal design that improve absorption performance relative to simple pipe configurations. Pontoon attenuators are the most common configuration in marinas and private dock applications where meaningful wave protection is required. They're available from multiple manufacturers in modular section lengths that allow the barrier to be configured to virtually any required length, and they can be fitted with deck surfaces that make the attenuator walkable, doubling as a perimeter dock or a wave barrier simultaneously. Bad attenuators use recycled tires, horizontally stacked and connected as a wave-absorbing medium. The irregular geometry of the tire stacks creates turbulence that dissipates wave energy effectively, and the rubber material absorbs the impact energy well. Tire attenuators have been largely replaced by purpose-built modular systems in new installations. But existing tire attenuator installations are still common on older marinas and some municipal launch facilities, and also in the ocean. They perform reasonably well, but are visually informal, difficult to maintain in neat condition over time, and not appropriate for installations where appearance matters. There are also moored vessel attenuators. In some configurations, a vessel, typically a barge or a large workboat, is moored in position to function as a wave attenuator. The vessel hull reflects and absorbs wave energy and creates a protected water area on its lee side. This is not a purpose-built attenuator solution, but rather a practical improvisation used in commercial and industrial waterfront settings. It's worth understanding conceptually because lake homeowners sometimes ask whether a large moored boat can substitute for a purpose-built attenuator. The answer is it can provide some protection, but the protection is incidental and inconsistent. The mooring requirements are significant, and the boat itself suffers accelerated wear from the continuous wave exposure it's absorbing. A wave attenuator under wave load is trying to move toward the protected area it's defending. The anchoring system is what keeps it in position, and the anchoring system is where most wave attenuator installation problems originate. Pile-anchored wave attenuators use driven or helical piles as fixed reference points, with the attenuator connected to the piles through guide brackets or chain connections that allow the attenuator to rise and fall with water level while restraining it horizontally. Pile anchoring is the most positionally stable configuration and is standard in permanent marina installations. The piles must be designed for the wave loads the attenuator would transfer to them, which are substantial in exposed installations. A wave attenuator in a high fetch exposure transmits significant horizontal load to its anchoring piles during storm events. Pile design for wave attenuator anchoring is an engineering calculation, not a rule of thumb estimate. Deadweight anchored wave attenuators use bottom weights, concrete blocks, chain masts, or purpose-built anchors, as shown in the diagram on the right, connected to the attenuator by chain or cable in a catenary configuration. The weight of the anchor and the geometry of the chain provide the restoring force that keeps the attenuator on station. Deadweight anchoring allows installation without pile driving, a significant practical advantage in jurisdictions where pile driving requires permits that are slow or difficult to obtain, or on lake bottoms where pile driving is impractical. The limitation of deadweight anchoring is positional compliance. A deadweight anchored attenuator moves somewhat toward the protected area under wave load as the anchor chain goes taut and the anchor drags slightly. In high wave energy environments, this movement can be significant enough to reduce protection performance and create hazards for boats and docks in the protected area. There are hybrid systems where some attenuator installations use a combination of pile anchoring on one end for fixed position reference and deadweight anchoring on the other for water level accommodation. Hybrid systems are common in installations with significant water level variation, where full pile anchoring would require complex adjustable connections on every pile. Wave attenuators are standard infrastructure in marina applications. The question most relevant to this audience is, when does a privately owned residential lake dock warrant a wave attenuator installation? The honest answer is not often, but in the specific situations where it's warranted, nothing else solves the problem as effectively. The primary factor driving wave attenuation consideration for a private dock is fetch exposure. Fetch is the unobstructed water distance over which wind can act to generate waves. A dock on a small protected cove with 200 feet of fetch is never going to face wave conditions that require attenuation. A dock on a large open lake with 2 miles of southwest fetch, where afternoon summer thunderstorms arrive from the southwest with fully developed waves, is facing a genuinely different wave environment. As a general framework, fetch exposures over half a mile in a direction aligned with prevailing storm winds warrant a wave exposure assessment before concluding that dock design alone can manage the conditions. Fetch exposures over a mile in exposed alignment are where wave attenuator conversations become practical rather than theoretical for private dock applications. The second major factor is the value of the boats using the dock. A dock sheltering a $15,000 runabout and a wave attenuator represent a questionable economic trade. A dock sheltering 2 or 3 boats with a combined value of $300,000 or more, the wave attenuator cost is a small percentage of the asset value it's protecting, and the calculus looks very different. Wave damage to boats at dock, chafe lines, dock line failures, boats pounding against dock bumpers, cleats pulled from holes is cumulative and expensive. A protected slip environment extends the life of dock lines, reduces wear on boat hulls and fenders, and eliminates the anxiety of watching the lake build during a storm and wondering what you're going to find when you get to the dock. A privately owned lake property operating as a vacation rental with dock access for guests has a different liability profile than a personal use property. Wave conditions that are an inconvenience for an experienced lake homeowner are a hazard for rental guests with variable experience levels and no local knowledge of how that specific lake builds in specific wind conditions. A wave attenuator that creates a consistently safe dock environment for guests of all experience levels is both a liability risk reduction and a rental property amenity that justifies a rate premium. The most common practical trigger for a wave attenuator conversation at a private dock is chronic hardware wear. Connection bolts that need replacement every season, dock bumpers worn through annually, dock lines that chafe through repeatedly, and float units showing accelerated impact damage. These are symptoms of a wave load environment that the dock is managing at the edge of its design tolerance. A wave attenuator that reduces the chronic load extends the life of every downstream component. Cost ranges for wave attenuators vary enormously based on length configuration, anchoring system, and installation complexity. Here's a realistic framework. Entry-level pipe attenuator installations. A simple pipe attenuator installation, 50 to 100 feet of large diameter HDPE pipe, deadweight anchored, can be installed in the $10,000 to $30,000 range, including materials, anchoring hardware, and installation labor. This is appropriate for modest fetch exposures and lower boat asset value situations where basic wave reduction is the goal. Mid-range modular pontoon installations. A modular pontoon attenuator installation, 100 to 200 feet of purpose-built sections, combination anchoring, typically runs in the $40,000 to $120,000 range. This covers the majority of private dock applications where serious wave attenuation is generally warranted. On full commercial scale installations, commercial marina wave attenuator installations, several hundred feet of engineered sections, full pile anchoring, walkable deck surfaces, navigational lighting, run from $200,000 into the millions, depending on length and exposure. This is not the private dock conversation, but it's useful context for understanding what the infrastructure actually costs at scale. Any wave attenuator installation that involves significant wave loads, pile anchoring, or a large protected boat asset should include an engineering assessment before installation. The engineering costs, typically $2,000 to $8,000 for a private dock assessment, is a small fraction of the installation cost and eliminates the risk of installing an undersized attenuator that doesn't solve the problem, or an anchoring system that fails under the first significant storm load. Wave attenuator installation almost universally requires permits. The permitting stack varies by state and jurisdiction, but typically includes some combination of the following. Army Corps of Engineers. Any structure placed in navigable waters of the United States requires a Section 404 or Section 10 permit from the Army Corps of Engineers, depending on the specific activity. Wave attenuators in navigable lake waters fall under this requirement. The permit process can range from a simple nationwide permit notification, appropriate for smaller installations with minimal impact, to an individual permit process for larger or more complex installations. State environmental agencies. Most states have their own water quality and shoreline permitting requirements that layer on top of federal requirements. State permits typically address impacts to aquatic habitat, navigation, water quality. Processing times vary from weeks to many months depending on the state and the complexity of the installation. Local municipality. Some lake communities have local ordinances governing dock and water structure dimensions, setbacks from property lines, and navigational clearances that apply to wave attenuator installations. The practical reality. The permitting process for a private dock wave attenuator installation is manageable but takes time, often 6 months to a year from application to approval for a straightforward installation in a cooperative jurisdiction. Budget the time as carefully as you budget the money. A waved attenuator you decide you need in July is not going to be in the water by Labor Day if you start the process in July. Wave attenuator installation is not a do-it-yourself project for most configurations. The sections are heavy, the anchoring requires underwater work, and positioning the attenuator accurately relative to the dock it's protecting requires planning and marine equipment. A professional installation crew with appropriate marine equipment, workboat, diving capability if needed, pile driving equipment for pile anchor systems, is the appropriate resource for any installation beyond the simplest pipe attenuator configuration in calm, shallow, easily accessible water. Section assembly typically happens on shore or on a staging dock before the attenuator goes in the water. Connecting modular sections on land where you have stable footing and full access to connection hardware is significantly easier and faster than trying to connect sections floating in open water with wave action working against you. Once the full attenuator length is assembled and floated, the structure is towed or walked into position. Temporary lines hold the attenuator on station while the permanent anchoring system is installed. For deadweight anchoring, this means deploying anchor blocks to the calculated positions and connecting chain runs to the attenuator. For pile anchoring, that means installing guide bracket connections to previously driven piles. Final positioning is verified from shore and from above, ideally with the drone, to confirm the attenuator is oriented correctly relative to the dominant wave approach direction and provides adequate coverage of the dock area it's protecting. A properly installed wave attenuator is low maintenance relative to the dock system it's protecting, but is not zero maintenance. Annual inspection should cover connection hardware between sections, bolts, pins, and chain connections that are under continuous dynamic load and need inspection for fatigue, corrosion, and wear. Hardware that looks fine at installation can show significant wear after a full season of continuous wave loading. This is not the same load cycle as dock connection hardware that sits relatively static between uses. Anchoring system inspection should verify that deadweight anchors have not dragged from their install positions, particularly after significant storm events, and that anchor chain has not developed kinks, broken links, or corrosion that reduces its load capacity. Pile guide brackets should be inspected for wear at the pile contact surfaces and for corrosion at hardware attachment points. Float unit or pipe section inspection should look for impact damage, cracking, and any taking on of water weight that suggests compromised buoyancy. A wave attenuator section that is riding lower than its neighbors has likely lost buoyancy and needs evaluation before it affects the attenuator's freeboard and protection performance. Navigational lighting, required on most attenuator installations, should be tested at the start of each season and inspected for impact damage, lens fogging, and corrosion at the mounting hardware. A navigation light that isn't working is a regulatory compliance issue and a safety hazard for boaters operating in low light conditions near the attenuator. In lakes with freezing winters, a wave attenuator faces the same ice risk as a floating dock, and the same decision about seasonal removal versus in-water de-icer protection applies. Most private dock wave attenuators in northern climates are either seasonally removed if the configuration allows it, or protected with de-icer systems sized for the attenuator perimeter. A wave attenuator that is damaged by ice over winter and loses sections or anchoring integrity before the spring season starts provides zero protection during the early season wave events that can be some of the most severe spring storms hitting a lake before the dock owner has been out to assess conditions and make repairs. Wave attenuators are one of those infrastructure decisions that lake homeowners either never think about because they don't need one, or think about constantly because significant wind events reminds them that their dock is fighting conditions it wasn't designed for. If you're in the second category, chronic hardware wear, boats taking a beating at the dock, guests on a rental property dealing with wave conditions that make the dock uncomfortable or unsafe, a wave attenuator is worth a serious evaluation rather than another season of managing the symptoms. The evaluation starts with understanding your fetch exposure, your wave environment, your boat asset value, and what protection performance you actually need. That's not a manufacturer conversation. Manufacturers will sell you an attenuator regardless of whether it's the right solution. That's an independent engineering conversation that starts with your specific site conditions and works forward to the appropriate solution from there. If you want a conversation, a Pennyvale Docks consultant covers wave exposure assessment, attenuator configuration options, anchoring system designs, and permitting pathway for your specific lake and property. Link is in the description. I hope this helped you understand how wave attenuators work. If you'd like a free Lake Dock Owner's Guide and a dock inspection checklist, scan the QR code. I'll see you in the next video.